Hello guys, this is Sahilkamboj and welcome to my YouTube channel Data Science Story. In the previous video, we have learned what is regression analysis and what is simple linear regression in particular, and we have learned we create the linear regression model using the Statsmodel library, and then we analyze the different parameters of the reports that have been published, that has been established by the Statsmodel, and we learn what's the significance of p-value and what is R-squared, what's the formula for R-squared, and then we learned how we can find the residual sum of squares, and then using the RSS we find the residual standard error. And all this knowledge that we have gained in the previous video, we will leverage this knowledge to get more understanding of creating multiple linear regression. Okay, so today's agendas of the videos is like we are gonna define what is multilinear regression and how to create multilinear regression using Statsmodel, and then we will analyze the summary report of that multilinear regression that we have created, and then we analyze the p-value that we have in case of multiple linear regression and the one that we have previously in the simple linear regression, and try to analyze the p-values of two different models, and then we try to find the accuracy of our multiple linear regression model using the standard residual error and the R-squared. And then we will see what are the different two extensions of the linear model, that is, one is additive assumptions and other is linear assumptions. We will also see how can we eliminate these two limitations of multiple linear regression model, and then we will try to understand the role of adjusted R-squared in comparing two different models, and in the last we will see the significance, how we can check or how we can compare significance of a model using the Fstatistics. Okay, so guys, let's start our today's video. So very first step is to we will install the important libraries that we will need in in creating the multiple linear regression. Okay, now it's we have successfully imported our libraries, and then we will import the data set, that is advertising data set, and this data set is also the same that we have seen in the previous video while creating the simple linear regression. And as I have told you before, that we just take these three columns as our predictors, that it's TV advertising budget, and this is the radio advertising budget, and this is the newspaper advertising budget, and these three predictors will be used to predict the sales amount in 200 different markets, and let's drop the unnamed column because we don't need it. And to create a multiple, first of all, let me tell you what is multiple linear regression. What's the difference between the simple linear regression and the multiple linear regression? So the very basic difference between the simple linear regression and the multiple linear regression is that in the simple linear regression we just have one predictor with respect to our output or response, that is sale. And in case of multiple linear regression, we will have more than one variable as a predictor to estimate the sales value. Okay, so this is the only basic difference, and you see here the equation that we are going to follow here is that sales is equal to beta naught plus beta 1 into my TV budget, and plus beta 2 into radio budget plus beta 3 into newspaper budget plus my standard error. So guys, let's first split our x and y, and these x and y we will later use in our stats model to create our first linear regression model. Okay, so let's estimate the regression coefficients of multiple linear regression using the stats model. So we have this report. So we're gonna analyze this report. If you see my previous video, you will find that in the previous video, let me show you. When we take only TV as our predictor with respect to our response, the Rsquared value is just 61%, and when we take all the three, that is TV, radio, and newspaper as a predictor, our Rsquared value has been increased to 89%. So this multiple linear regression model has successfully able to explain more variability of the data set than the simple linear regression model. Okay, so let's have a look of the, and if the very important observation here, if you can find, is that when you see the p-values related to the different three predictors, and if you see the p-value related to TV, it's 0.000. I'm going to tell you that you should always aspire for this value. Look for the p-values where there are three zeros after the decimal. And what p-value signifies that if the p-value is less than 0.05, then that variable has significance for our model. Okay, and you can see the p-value of the radio, it's also 0.000. But when you see the p-value related to the newspaper, it's 0.0860, and it is not less than 0.05. What it signifies that when we use newspaper along with other two predictors, that is TV and radio, it has lost its significance for our model. Okay, so let me clear on you guys on this point. You see the results of here, the simple regression where we just take the radio and as a predictor and sales as a response, and then here where we just take the newspaper as a predictor and sales as a response. And if you analyze the p-values of these in case of simple linear regression and in case of multiple linear regression, you will find that when we use newspaper along with others predictors, it's not gonna stay a relevant predictor anymore. But when we use as only single predictor newspaper, it's we not gonna find this significant observation. Okay, so guys, it means that our multiple regression model is suggesting us that there is no direct relationship exists between newspaper as a predictor and the sales. Okay, but this thing is not able this thing is not clear when we use just newspaper as a single predictor. So after comparing the p-values of simple linear regression in case of newspaper and the multiple linear regression for the same newspaper, we found that there is no direct relationship between the sales and newspaper. And you can get the idea from one more examples that I'm going to give here, guys. If you see the correlations of the different three different predictors with respect to the sales, you will find that newspaper has kind of more relationship to the radio. So this implies that there is more tendency to spend on newspaper advertising in markets where more is spent on the radio advertising. Okay, so newspaper spending advertising budget is related to the radio advertising budget, So you can get a clear idea that I'm going to tell you from one example here. So let's suppose a data set where there is a beach, and the more the number of sharks attacks, then there is more the number of ice cream sold. And if you take only these two, that is ice cream sale and the shark ice cream sale as a predictor, and ice and sharks attack as our response, you will find that uh, you will feel that you can imply from it that the more the ice cream sold, then there is more the number of sharks attack on the people. But that is not the case in reality. So if you take temperature as a one more predictor in your equation, and you create a multiple linear regression, you will find that actually that is the temperature that is directly responsible for the more the number of sharks attack on the people, because as the temperature increase, then there is more number of visitors that visited that particular beach, and then that is responsible for the more number of sharks attack on that particular beach. But you will show, so you find that more the selling of ice cream is not directly related to the sharks attack, but it's in reality that is the temperature as a predictor that is directly responsible for the more the number of sharks attack. So the same scenario is here, guys. And if you create a single linear regressions, simple linear regression, and taking just one of these predictor in that simple linear regression, you will not able to judge that this kind of relationships in our data set as a whole. So from here we can just finally concluded that newspaper is not anymore a good predictor for our data set. We can just simply drop that newspaper as a variable in our data set, and will create our multiple regression model using just two predictors, that is TV and the radio, for our sales. So let's take some important questions that we want to answer while creating the multiple linear regression. So first question is that is at least one of the predictor of the TV, radio and newspaper is useful in predicting the response? And the second one is, does all the predictor help to explain the why, that is sale, or is only a subset of the predictors are useful? And the third question is that we are going to answer is, how well does the model fit the data, or how accurate is our prediction? So the answer to the first two questions is that there is not the case that all the predictors are helpful to explain our why, but the subset of the predictors, that is only the TV and the radio, are useful for our multiple regression model. So we are gonna just drop the newspaper as a variable here, and our equation will be transformed to just take two predictors, that is TV and radio. So let's create our new regression model where we just take these two predictors. And if you see the compare the R value, you will find that there is no difference between the R squared value, and there is also no difference between the adjusted R squared value. See here. So we have successfully get rid of a variable that has no prediction value for our model. Got it? So the next question that we are going to answer, how well does the model fit our data, or how accurate is our prediction? So as I have already explained you how we can assess the accuracy of model, there are two methods. One is R squared and the other is our RSC, that is residual standard error. So to find the standard residual error, you have to first get those values, those predicted values for the sales, and this is the case that I have done in this particular line of code. I have just created a column, that is y hat, that is the predicted values of the sales, and just use the coefficients of TV and radio here, see, and the constant coefficient here, and just create that multiple linear regression fit line. And to find the this is the formula, guys, that I have already told you guys in my previous video. Please, if you haven't seen my previous video, please have a look on that. You will get the concepts of what is RSS, what is RSC, and I am just using the those formulas here. And what is residual sum of squares? It's basically the difference between the predicted value and the actual sales value, and then do the square of the that value, and then just do the summation of all these value, and you will be presented with the RSS. And if you finally we want to calculate the residual standard errors, and here the n is 200 because there are 200 observations in our data sets. And you can also find the shape of the data set, and you will find the value for n. See, okay, got it. So there are 200 observations in our data set, so n is equal to 200. Then we just use the numpy to do the square root of the RSS and divide it by n-2, because this is the formula that we have seen in our previous video, and just do dot round, use the dot round function to get the values up to 2 decimal. So as we have previously seen, this means that the actual sales in each market deviate from the true regression line by approximately, if you multiply this by 1000, 1680 units. And you can also find the percentage error by just dividing this value by the mean of the sales value, and you will find that now the percentage has been error has been reduced to 12%. Earlier it was, when we take TV just as our predictor, it was 23%, and now we have successfully created a better model than the simple linear regression model. And then we just create a data frame that contains the R-squared value and the RSC value. So I hope I am able to clear you guys on this, how you can assess the accuracy of a model using the residual standard error. And the next concept that we are going to learn here, that what are the extensions of the linear model. So the one thing you need to understand, that our standard linear regression model provides us very interpretable results and work quite well on many of the real world problems, but it assumes number of important assumptions for a data set to have. And the two of the most important assumptions that states the relationship between the predictor and response are, the one is additive assumption and the second one is linear assumption. So guys, what is additive assumption and how we can get rid of this? Additive assumption, that I will take the example of our data set, that is advertising data set. Additive assumption is that the effect of the changes in a particular predictor, let's say the TV, on the response, say the sales, is independent of the values of other predictors, that is the newspaper or the radio. So it assumes this kind of relationship in our data set, but this is not always the case in the real life example. In real life, so let's take our data set as advertising. It possible that let's first me write this code and have a visual of our data set data.head. It may possible that in reality, guys, the changes in the TV budget may have a certain impact on the newspaper budget. Let's say it may possible that if you increase the budget of the TV as a source of media advertising, it may possible that the newspaper advertising budget in that particular market will have to decrease, because the overall budget advertising budget is constant. Okay, so I hope I'm clearly able to understand you this concept of additive assumption. So how can we get rid of this additive assumption, guys? So we just by just adding an interaction term that include those two predictors that have that are not independent of each other. So let's say we have the x1 that is TV and x2 that is the newspaper. Then we add just a third term that includes both the TV and the newspaper, and then we use this equation to find the new multiple regression model. So to create a new multiple regression model that includes the interaction term, we first have to create a predictors that includes the value of the radio and the TV advertising budgets, and this can be created using this line of code. We just use the data, and that includes this column, and this column includes the values that has the multiplication of the TV value and the radio advertising value, and then we just create the split of x and y, and then we just create the multiple linear regression model using the Statsmodel. And if you observe the R-squared value, guys, here first, you will find that now our new multiple linear regression model that has the interaction term is able to explain the 96.8 variability of the data set, and that is the huge jump from our previous model that doesn't have that interaction term. So we successfully able to get rid of this additive assumption. And if you look into the p-values of our newly created predictor that contains the values of both TV and radio, it's 0.000, and this tests our hypothesis that the newly created predictors, the constant related to the newly related predictor is not equal to 0, and we accept our alternative hypothesis, and it signifies that our newly created predictor has a significance value for our model. And if you want to see the correlation of the newly related predictors with respect to the TV and with respect to the radio, you will find they have highly correlated, and this same thing is shown here, that our model is telling us that this might indicate there is strong multicollinearity or the other problem. Okay, so guys, our model, the previous model has some kind of additive relationships, but by adding the interaction term, we are successfully able to get rid of that. And if you do this math, that these are the R-squared value of our new model, that is 96.8, and this is the R-squared value of our previous model that doesn't have the interaction term. And you will find that 69% of the variability in the sales that remains after fitting the additive model has been explained by the interaction term that we have added. So guys, in conclusion, we successfully able to create a better model using the interaction term. So next step is to check the linear nonlinear relationships and how we can remove them. Remove, I have misspelled. Okay, so first we will check the relationships with respect to the TV and the radio, and with respect to TV budget and sales, and with respect to sales and radio budget. We will see that these two predictors has kind of linear relationship with respect to the sales. So to understand this concept of non-linearity relationship existence in the model, we will take another data set and where we find this non-linearity relationships and try to remove them. So I'm using here the real life data set of auto sector, and you will find this data set on the ISLR book, or you can also load this data set from the sklearn data sets. So I am here, what I am doing here, I'm just taking the horsepower as our predictor and MPG as our response, or you can say dependent variable, and horsepower our independent variable. And when I'm analyzing the values of horsepower, I found that this question mark, there is number of columns, number of rows that have this question mark punctuation, and by writing this line of code, I'm just excluding those rows, okay, so that I get the clean data set for my further analysis. And if you check data.info, you will find that our response, that is dependent variable, has a float data type, but our horsepower is of object data type. So to do the algorithm of the multiple regression to work, we first have to change this data type to integer data types. And why I'm taking the integer, because all the values in the horsepower are no and none of the value in the horsepower is of decimal. So after changing the data type, I am just checking what kind of relationship is present between the horsepower and the mileage per gallon. You can clearly see, guys, there is some kind of curved relationship exists between the horsepower and the our dependent variable, that is MPG. And in the previous data set, this is not the case. Both the predictors has kind of linear relationship. So when you get this type of situation in your problem, what you can do is that you just try to estimate that this relationship, not the straight line, but by transforming that straight line into some kind of curve. Okay, so first we will create a model that has not include this limitation. So I'm just taking the horsepower as our x and y as our MPG and try to make a simple linear regression model. You will, and then I will analyze the R-squared value and the coefficients related to the horsepower and constant. I will find that their p-values is 0.000 and 0.000. So it means that both the constant term and the horsepower are significant for my model. And I'm gonna plot this regression fit line that I have now created using the matplotlib.scatter. And so this is the regression line that I have just created using the Statsmodel. And you can clearly understand by analyzing this graph that our model is not capturing the real relationship that exists between the horsepower and the MPG. So our real relationship has some kind of curve here, you see, but our created model uh, doesn't explain this curvature in its regression fit line. So how we can get rid of this kind of problems? So one thing you can do, that you can just transform your simple linear regression equation into a quadratic equation, and that quadratic equation can be of different up to of different degrees of coordination. I'm trying to say you here is that a simple approach for incorporating a nonlinear association in a linear model is to include transformed version of the predictors in a model. So we are going to transform our horsepower predictor here, and for example the point is to have a quadratic shape, and suggesting that a quadratic model of a form may provide a better fit. So I'm just including this term that has the horsepower square as a value in our previous model. Okay, and gonna convert the simple linear regression into the multiple linear regression model. So to do this, guys, I'm just first gonna create a new predictor that has the value horsepower square with this line of code, and after that I'm taking the x that include the both these two values, that is horsepower and horsepower square, and the y that is our mpg, and let's create our new multiple linear regression fit. And if you guys analyze the r square value of this newly created model, the quadratic fit appears to be substantially better than the fit obtained when we just take the linear terms is included in our simple linear regression model. See, the r squared value is the previous r squared value is 0.606, and the newly created model has value is 0.68. So our model has able to explain more valid variability of the data set. And this approach that I have just described here to extend a simple linear model to accommodate the non-linear relationships is also known as polynomial regression. And because since we have included a polynomial function of the predictor here, and guys, if you see the p-value related to our newly created predictor, that is horsepower square, you will find the 0.000, and this signifies that the null hypothesis, that is the coefficient related to the horsepower square, is equal to 0, and the alternate hypothesis that the coefficient related to the horsepower square is not equal to 0. So we gonna successfully able to reject our null hypothesis and accept the alternate hypothesis, and it implies that our newly created horsepower square is significant for our model. So guys, if you now I'm gonna plot the newly created multiple regression fit line with respect to our data set, and you find this is our newly created estimation of the real relationship, and you will see that we successfully able to imitate the real relationship that exists between the horsepower and mileage per gallon. So guys, next concept that we are going to do is try to understand the role of adjusted R squared. So I haven't told you about this parameter that is what it does for our model, how we can compare the two models using this using the value of adjusted R square. I am just taking our previous data sets and gonna create a simple linear regression fit using the stats model, where I take the TV as our predictor and sales as our dependent, that is response. And now to understand the concept of the role of R squared, I'm just create a predictor that has nothing to do with the sales. I'm just create a random numbers and up to 200 for 200 observation, and you will find this here. And I'm gonna now create a multiple linear regression model that includes the two predictors, that is the sales and our newly created superficial predictor, that is random 1 2 3, and try to create a multiple linear regression model. So guys, and when we take this superficial predictor, that is random 1 2 3 in our model, you will find you just observe the R-squared value. The R-squared value of our newly created model is 0.612, and the R-squared value of our previous model is also the 0.162. But when you see the value of adjusted R-squared, you will find that there is decrease in the R-squared value, adjusted R-squared value in our model, that include the superficial, or you can say the predictor that has nothing to do with our output, that is sales. And this implies that the R-squared, the formula that includes in the R-squared, actually penalize those predictors that has not any significance of prediction for our model. So from here you can imply that when you take the random 1 2 3 as a value as a predictor, it actually decrease the predictability power of our model. And you can also get the idea of its significance when you check the p-value and it's greater than 0.05, and it also implies that we can't reject our null hypothesis that the coefficient related to the random 1 through 1 2 3 is equal to 0. So we have to accept the null hypothesis, and we have to take that the coefficient related to the random 1 2 3 is actually equal to 0. So the predictor random 1 2 3 has nothing to do with our model, or you can say our dependent variable, that is sales. So I hope you guys understand how we can compare two models using the adjusted R-squared value, and also check the significance of a particular predictor using the p-values. So guys, next thing and the last concept that we are going to do here in our video, that is how we can test the significance of a model using the Fstatistics. Okay, we the basic guys difference between the p-values, that is the here, and that these are the Fstatistics value, is that p-values tell us the significance of a particular predictor for our model, and the Fstatistics tells us the significance of a model as a whole. Okay, so to understand the role of Fstatistics, we're gonna create our same scenario as we have created here for understanding the role of adjusted R-squared. We just create a superficial predictor, that is random 1 2 3, and first check the model that has only TV as a predictor. You will find the Fstatistics that here is the value of Fstatistics is 312, and the value of Fstatistics in the model that has the random 1 2 3 as a predictor is almost half of the values that we have seen in our previous model. So what does this implies? And if you see the values related to the probability of statistics, it's 0.147 into 10 to raise power minus 42, and in our new model that include that superficial random 1 2 3 has a probability of statistic value is equal to 2.10 into 10 to raise power minus 41. So it actually increased so it's like the p-value. Okay, so it's actually increased, but these two values are almost equal to 0, and when you see the f statistic value, it's actually got decreased by half. And what does implies when we compare these two models, that our model significance has been actually minimized when we use the random 1 2 3 as our predictor, one of our predictor. And when you check the p-value, guys, you can also get an idea that the p-value related to the random 1 2 3 is actually greater than 0.05, and this implies that we can't reject the null hypothesis, that is the coefficient related to the 1 2 3 is equal to 0. So we have to make the coefficients and of the random 1 2 3 is equal to the 0 in the our multiple regression line fit. So what is f statistic, guys? Actually, it is much like that, like the z statistics that follows the normal distribution, and the t statistics that follows the teacher's distributions. F statistics follows the, that is f distribution, and it can be used to compare two different models to check their significance. Okay, it's useful for the hypothesis testing. So what's the hypothesis testing that we are going to check here is that here our null hypothesis is that the coefficient related to all the predictors is equal to 0, and the alternate hypothesis here is that at least one of the coefficient related to any of the predictor is not equal to 0. So if all the betas are 0, then none of the x matter to our y, and our model has no merit. Okay, and if at least one of the predictors has coefficient that is non-zero, then at least one of the predictors has related to our response, that is y. So from here we can conclude that the model without the random 1 2 3 as a variable is more significant than the model with the random 1 2 3 as a variable. So that's all that I have for this video, guys. I'm just gonna give you the recap what we have learned today. We just take the advertising data set that contains the value of 200 different marketplaces, and with respect to their sales and their advertising budgets, we actually have to use the advertising budgets related to 3 different media and predict the sales value of the product here. And then we just create a simple or you can say multiple linear regression model that includes all the three different media budgets, that is TV, radio and newspaper. And then we analyze the p-value related to all the 3 predictors, and we find that the p-value related to the newspaper is actually more than 0.05, and we have to accept the null hypothesis that the coefficient related to the newspaper is actually 0, and it has no significance for our model, and we drop the newspaper as our predictor. And we find that newspaper is actually not directly related to the sales. And then we just try to answer these 3 different questions, and where we answer that actually there is not the case that all the predictors are helping us to explain the why, that is sales. Actually there is subset of the predictors that we include only TV and the radio as our final predictors to create our final multiple linear regression model. And actually we able to create a better model using just these 2. And then we try to assess the accuracy of model. And here we just try the knowledge that we have acquired in our previous lecture while we are understanding the basic concepts of the regression analysis. And we just find the residual standard error, and it's actually half of the residual standard error that we just created in our simple linear regression model in the previous video. And then we just try to eliminate the two assumptions, that one is additive and the other is linear assumption, and we can eliminate the additive assumption just by adding an interaction term that includes the both predictors, that is TV and radio in our case. And then we find that our model predictability has been increased and the R-squared value has been jumped to 96.8%. And then we also check the p-value related to our newly created predictor, that is TV into radio, and it's mean that we have successfully able to create a significant predictor for our model. And then we check the non-linearity relationships, and for this we just take another data set, real data set, that is auto, and we just take we create a simple linear regression model using the horsepower as our predictor and MPG as our response, or you can say dependent variable. And then we just check the scatter plot, where we visually find that actually there is the relationship, the real relationship between the horsepower and MPG is actually not linear. It's actually a curved kind of a relationship that exists between our predictor and the you can say the response. And we then create our simple linear regression model by just taking the horsepower, and we will find that it's actually not able to imitate the the real relationship, that is the curved relationship that exists between the horsepower and MPG. So to imitate the real relationship, we just we just transform our simple linear equation into the quadratic equation by just adding a polynomial function that includes the values of horsepower square, and then just try to create a new model, and we will able to create a new better model than our previous model. And when we check the p-value related to the horsepower square, it's actually 0.000, and we successfully able to reject our null hypothesis and accept the alternate hypothesis, that is the coefficient related to the horsepower are not equal to horsepower square are not equal to 0. And we also are able to increase the R-squared value and able to increase the variability explanation of our model by just including that quadratic fatal equation. And when we observe the newly created model in the scatter plot, we find that we successfully able to imitate the real relationship that exists between the horsepower and MPG. And then we try to understand the concept of adjusted R-square, and how we can use the knowledge of adjusted R-square. And we found that the equation that is used to calculate the adjusted R-squared actually penalize the model that has a predictor that has no significance for our model. Okay, so the same thing is we understand in case of Fstatistics, and the difference between the p-value and the Fstatistic is that the p-value just tell us the significance of a particular predictor, and the Fstatistics tell us the significance of a model as a whole. So and in p-statistics we found that the hypothesis that we test here, that the null hypothesis is that the value of all the betas is equal to 0, and the alternate hypothesis is that the value of at least one beta is not equal to 0. So here we successfully able to accept an alternate hypothesis, and we found that the model without the random 1 2 3, that is fake predictor variable, is more significant than the model that has the variable that is random 1 2 3. So this is all guys that I have for this video. I hope I able to understand you guys some basic concepts of the linear regression, and if you have any doubt related to this particular concepts that I have teach you, please comment in the comment box. I will try to give answer to those questions. And if you like my videos of or way of teaching, please subscribe to my channel Data Science Story, and please like my videos. It will give me more motivations to make more videos for you guys. And if you want to any video on any topic, please let me know just by either mailing me or just by writing in the comment blocks below. So thank you guys, thank you very much. This is Sahil Kamboj. Bye bye, tata.